Welcome to the Theta Oilfield Services Rod Pumping Optimization video podcast. This is John Svinos. Let's discuss how to analyze and to redesign and rebalance an existing rod pumping system. Typically, before we start to do the analysis with XDIAG, we need to run XBAL if the data is available. So let me do that. Let me bring in XBAL. In this case, I already put the data for this well, which has it's a Lufkin Mark II 168 108 MRO cranks with these counterweights. They're all at the end. These two weights have auxiliary weights. That's what the red outline indicates. And the maximum counterbalance moment for the existing counterweight configuration is 1788.8 thousand inch-pounds. So this is the first step in the process of analyzing the well. By running XBAL first and by putting in your existing crank and counterweight information, then we have the existing counterbalance moment, which we can then use in XDIAG to tell us what the existing gearbox loading is. So now I'm going to minimize XBAL. We're going to get into XDIAG. So this is the data for this well. I'm going to advance through the input windows. A previous podcast on how to use XDIAG is available on our website if you would like to go watch that first if you are not familiar with how you run XDIAG. But basically at the pumping unit input window, actually I can go directly to it, we can select here get XBAL information, and we can select to use the information that XBAL placed on the Windows clipboard, which is this value that we saw in XBAL, so that the program knows what the existing counterbalance moment is. So now when we run XDIAG for this well, it will tell us what the gearbox loading is for the existing conditions. Okay, here is the expert diagnostic analysis report from XDIAG. The program says there is severe fluid pound here with 55% pump fillage. There are 5.7 inches of tubing movement, which is maybe due to a malfunctioning tubing anchor. XDIAG has determined the fluid level to be at the pump, which corresponds to a pump intake pressure of 60.4 psi. And it's also warning us that the results in this case may be unreliable because the dynamometer data contains too few points. Please see the input data analysis section for more details. So in the input analysis section, it says that the dynamometer card contains only 50 points, and the program recommends at least 70 points should be used for more accurate results. Here under surface equipment analysis, we see that the gearbox is overloaded by 19%. The pumping unit is slightly out of balance, and the gearbox is undersized since it would be overloaded by 13% even after balancing the unit for minimum torque. Let's page down to the next page. This is the system design score. This uses the technology that we first developed in the XROD program. We get a score of 60% or D. Why do we get a score that is D? Well, this page explains why that is. The gearbox loading score is only 10 out of 100 because the gearbox is severely overloaded. The ideal range for the gearbox loading should be between 70 and 95%. Another reason why we got a lower score is because the structure loading score is 30. That's because the structure is overloaded at 107%. And again, this number needs to be between 70 and 95%. And we got a 90 on system efficiency because our system efficiency is 40.6%, which is good, but it could be better. And also for the bottom minimum stress, we got a score of 30 because the bottom of the last section on the rostering is in compression, and we need to keep that stress on the bottom of the last section above the single bars between 300 and 650 to avoid any possibility of buckling. So if I take a look on the next page, I can see here what the problems are. The gearbox is overloaded, the rods are in compression as the program indicated. But you know, let's go back to this window here. The program says here that the gearbox is severely overloaded at 134%. Now, if you look on the next page, it looks like the gearbox loading is only 119% loaded. So you might say, well, why did it say that it was 134% loaded? Well, if we go back to the previous page, look what it says here. System design score for full pump and fluid level at the pump. So in other words, this page here in XDIAG gives you the system performance or design score under worst case conditions. So for a full pump and fluid level at the pump. In this case, as you can see from the dynamometer card, the well is pumped off. It does not have a full pump. So that's why the gearbox loading is not the same as for a full pump. So if we go back to the report here, if we look at the third page of the report, we see that the system efficiency here as it exists is 37%. That's how the system is running right now. The gearbox is 119% loaded, and if we balance it, the best we can do is 113%. Now the well is making 326 barrels a day right now, and it has a pump fillage of 55%. As you can see here, and the rods are in compression. Actually, they're not in compression in this case as it exists, but according to what the report said here, the rods would be in compression if the pump was full. Okay, so what can we do to improve the operation of this system? Well, obviously we need to do something about the gearbox being overloaded. We also need to do something about the rostering if the pump is full. But since this well is pumped off, that means that it's already getting all the production that there is to get for the well, which is about 326 barrels a day. So we need to maintain that production, but not necessarily the way the unit is running. The unit right now is running at 14 hours a day. There's really no reason why it should be running 14 hours a day. The reason why it's doing that now is because it's oversized. So we have more capacity in the system, and we can get more production as compared to the production that is available from the well. So what we need to do here is save the results of XDIAG by clicking on Quick Save. And now what we will do is we want to launch XROD and load this case into XROD. The way you do that is you select Open File from XROD. For the file type, you select XDIAG, and then you go to the directory that contains that file. So I'm going to go find this case. Okay, here it is. The program says that XDIAG corrected a load shift. Do we want to bring in the corrected card? I want to say yes. Okay, so now the data from XDIAG has been brought into XROD. Now, when you do this, you're going to be in the non-AI mode. I forgot to mention that. In other words, you click on this button here until you see this icon show up, and there is no indication here that says AI mode. That means you're in non-AI mode, which means that you're in the same mode as Rodstar V. So since we probably don't want to change the pumping unit if we don't have to in this well, we're going to try to keep as much of the equipment as possible. The first thing we want to do is select full pump, because we want to design the well for a full pump. And in the next input window, instead of the existing pumping speed of 9.5, we can select to enter a target production. Now we know the well is making 326 barrels a day, but we probably should try to increase the target production slightly in the design. Maybe instead of 326, we'll make it 350. That way we can ensure that we are getting all the fluid that is available. So we're going to put that as our target production. That way the program will calculate the pumping speed we need. Okay. Oh, and the program actually reminds me here that my pumping speed is still 14 hours. So it's asking me, do you want to achieve this target production with a runtime of 14 hours? I'm going to say no to that, and I'm going to change this to 24 hours because I want to be able to get all the production without getting into fluid pound. So I'm going to select 24 hours, 350 barrels a day. For the pump size, since the gearbox is overloaded, I probably don't need a pump this big. Since I have excess capacity, I'm going to let the program calculate the plunger size for me, and I'm going to select insert pump. I don't think I need the tubing pump. So let's see how that works. Now the rod string I'm going to try to keep as it is for now, but later I'm going to also check to see what is the ideal rod string design for this well. That way the next time the well, the rod's part, I can go in with a better design. But for right now I'm going to keep it as it is. The same thing for the pumping unit. Now I could try keeping it at the 168-inch stroke, but since the gearbox is overloaded and since I have excess capacity, I really don't need to stay at the long stroke length. It probably would be a better idea to go to crank hole number 2. So let me do that. Also, the existing counterbalance moment, even though that's useful for what the unit is doing now, I really don't care what that is, since if I'm going to redesign the unit, I'm going to have to rebalance it anyway. So I'm going to say unknown for that. Let the program calculate what I need. Okay, and here I'm going to keep the motor size as it is. I'm going to include speed variation here, and now I'm going to run the program to see what the results will be and what my score will be when I change the speed and the pump size and the stroke length. So even though I'm running XROD in the non-AI mode, it's still going to generate a score for me, and also it will tell me what I need to do to improve my system performance. So here I'm getting a B+, which is already better than the D score that I had before. It says the rod loading is very low at 59%. So in other words, my rods are over-designed, basically. My system efficiency is kind of poor, and the single bar section may be longer than it needs to be, since I only need to be between 300 and 650 psi. So let's take a look at the numbers here on the report. I'm getting the production I need at 24 hours a day. My pumping speed is 8.12 strokes a minute. My gearbox is 76% loaded. My pump size is 1 3/4 inch. And here is my rod string, the existing rod string, which is a little bit over-designed, of course. Now, one of the things I can do to improve my efficiency is to, I can go back to the tubing pump that I had. As a matter of fact, since the pump is, there's nothing wrong with it really, I could actually keep that as it is for now. So let me go back to that. So I'm going to select tubing pump, 2 1/4 inch plunger size, just like I had before. And I'm going to make another run to see if my efficiency will improve with the existing pump and if the rods and gearbox are still okay. Okay, now I'm getting a B+ design. The rods are still okay, and it looks like my efficiency actually improved considerably by using the larger pump. My pumping speed is only 5.28 strokes per minute. So this is actually a better approach, I think, here. So I'm going to keep that tubing pump that was in the well in the first place. The gearbox loading is now 86%, so I was able to fix that problem by using crank hole number 2 and by slowing down the unit. And it looks like the single bars are still an overkill situation here. You know, we have too many single bars at 825 feet because the bottom minimum stretch on the 7/8 here is 49.97, so that's quite a bit high. But since the rod string already is in the well, I don't want to change it until I have a part. Now, I could actually, if the rods are fairly new in this well, I could use these rods in another well and put the appropriate rod string in this well that would better match the capacity of the system. If I want to do that, what I would do is I would go to the rod string window, and instead of this rod string, I would have the program design the rod string for me. Now, I don't think I need Weatherford electro rods here because my loading is not that high. So I'm going to go to maybe grade D rods, API grade D rods. Okay, 1 inch to 3/4. And I'm going to include single bars on the bottom. I think 1 3/4 inch single bars are too big, so I'm going to go with 1.5 inches. And I'm going to have the program design the single bars for me. That will save me time. So I'm going to go ahead and run it again. Okay, now I see that actually the rods are slightly overloaded. So I may have to go to stronger rods anyway, but everything else is okay. So if I take a look at the report here, yep, I see the problem here. They're slightly overloaded. Not too bad really, but to avoid being overloaded, I can go to, let me go back to Electra rods. And try that. Let me run that run again. Have the program design the single bars and the rod string for me. Okay, now I'm getting an A+ design. The only problem here is that my structure loading is kind of low. Well, that's okay. You know, that's not that critical. I don't want to go change my pump unit just for that. So it looks like in this case, with a 2 1/4 inch plunger, my efficiency will be very, very good. 47%. My structure loading will be 66%. My gearbox loading 83%. And I only need 3/4 inch rods all the way with 325 feet of single bars on the bottom to get the 350 barrels a day that I need at 24 hours a day. Now there is one last thing I want to do here, just to make sure that if I get into a fluid pound situation again, I have the right number of single bars here. So what I'm going to do is I'm going to go to the rod string window. Instead of selecting to design the rod string, I'm going to select manual rod string entry. The program will take the existing rod string design and put it in memory. That way this design will not change, because basically what I want to do is I want to test this design for fluid pound conditions. So I'm going to go here to my first input window. Instead of a full pump, I'm going to select fluid pound, and I'm going to put I'm going to test 40%, 50%, and 60%. Well, actually, it depends really how you set up your pump off controller. For example, if you set your pump off controller to shut down the unit at less than 75% efficiency, let's say, or fillage, then I really don't need to go to the lower fillages. I can start with, let's say, 60%, because in some situations, since we have to experience 2 or 3 cycles of fluid pound before the pump off controller will shut the unit down, sometimes the fillage could get to that lower level. So at first I'm going to try 60%, and here the program is using the same pumping speed that it had come up with before. So now when I run it, let's see if the rods might go in compression when I have fluid pound, which would indicate that I need more single bars. Okay, let's take a look. Nope, I'm still going to be okay. So that's not going to be a problem. So now, I don't really care about anything else in the report at this point. That's really the only reason I'm making this run, is just to check to see if my bottom minimum stress would be negative if I go into fluid pound. So I'm going to go back here. I'm going to change my fillage to 70%. Try that. Actually, this is a Mark II pumping unit, and we have found that for Mark II units, sometimes the worst fluid pound is actually like around 90% or so. So I'm going to check that to see what happens around that fillage. Again, let me check my single bars. They're still okay. Go back again. And I'm going to put 80% fillage. Run it again. Okay, we're still going to be okay there. But now what about 90%? That's the one I'm concerned about. Let's run that again. And actually, even at that fillage will be okay. So it looks like this 325 feet of single bars is what we need. There'll be no problem at different fillages that we might experience when we have fluid pound. So I'm going to go back here and I'm going to select full pump, 85% efficiency, and keep that same target production of 350. And this rod string is the same as what the program came up with. So let's see what my final design is going to look like. Okay, so I'm getting a 98% now, A+. That's much better than what I was doing before. Everything looks fine. Nothing is overloaded. And I have the right number of single bars. So now all I need to do is balance the unit, and I'm ready to go. I just wanted to point out the before and after benefits of doing this. Obviously, not only will the gearbox not be overloaded and the efficiency will be better, but also look at our lifting costs. Our lifting costs now are $1.66 per barrel of oil, and let's see what they were before. Let's go to XDIAG. Before they were over $2 a barrel. They were 2.11. So I would say we've improved the situation quite a bit by going to $1.66. Okay, so now to balance the unit for these conditions, I need a counterbalance moment of 1268.45, as you can see here. Okay, so how do what do I need to do with my counterweights to achieve this maximum counterbalance moment? Well, the first step is to export this value back to XBAL. The way you do that is you go here on the toolbar, click on the button to export this value to XBAL. You click OK, then you go back to XBAL. And in this and now, we have something to put in here under the balanced condition. So I could type that in, but it might be quicker if I just click here, import maximum counterbalance moment. That brings the value that I need into this field. And now the program says that I need to move, let me resize this here. I need to move all weights to 29.03 from the end to balance the unit. So that's my solution. And once I balance the unit, all I need to do to update this file is to click on option number 1 here. The program asks me, are you sure you want to move the weights to the positions in this column. I'm going to say yes. It's going to move them for me, and now I can save that file, so the next time I need to do this work, I already would know what my existing counterbalance moment is. And before resaving it, I can delete that balance moment, which I will not need next time, and then save that program, save that file. So that's how this process works. So that's how we calculated the counterbalance moment we need to balance the unit, but also we need to lower the pumping speed here from the original pumping speed, which, let's see what it was from the XDIAG program. It was 9.52, and now it's 6.11. How do we accomplish that lower pumping speed of 6.11? Well, what I'm going to do now is, first I'm going to save this XROD file, which is actually a RODSTAR file, because when you run XROD in the non-AI mode, it actually works like an enhanced version of RODSTAR, and it saves the files as RODSTAR files. So I'm going to select to save that file, and I'm going to name it the same as the well name. I'm going to save it, and then what I'll do is I'm going to launch XTOOLS to allow me to find out what sheave size I need to change my pumping speed. Now, one nice feature in XTOOLS is that you can load a RODSTAR file with the data that you need, and I'm going to show you how that can save you a lot of time. Okay, so here is XTOOLS. We are going to run this module, the module to calculate the sheave size that we need. So I'm going to click on that, and that will launch the window for that module. Okay, so now instead of having to type all this in, what I'm going to do is I'm going to click here, Use File, and I'm going to select a RODSTAR V file, and then I'm going to go to the directory that contains the file that I want to load, which is the file that I saved from XROD. So there it is. So when I bring that in, as you can see, it fills in all the information. It puts in the pumping unit manufacturer, the year, gearbox size, well name, and so forth. I just want to make sure that I have the right sheave gearbox diameter. Okay, so you know this is something you have to check in the field to see what you have. These are all the available sheave types and sizes for this unit. So let's say I have this one, the 55.6 inch 6C type sheave. This is the pumping speed I need, 6.11. Okay, my motor is 75 horsepower NEMA D. So all I need to do is click here, calculate motor sheave diameter that I need. So the program says to achieve an SPM of 6.11, the motor sheave diameter should be 8.45. The closest commercially available sheave is 8.5 inch, and the resulting SPM would be 6.15. So that's very, very close to what I need. So this is the shift size that I need, is 8.5 inch. So that's how easy it is to determine that. Now you may remember that the XDIAG diagnosis said that the tubing anchor may be malfunctioning here. So how do we make sure that the tubing anchor is set correctly in this well? Well, there is another module that we can call up. Let me close this module here. Tubing anchor calculation module. If I launch that, all the data is still from the well that I loaded is still here, and I just need to put in the missing information. So what is my static fluid level from surface for this well? Well, let's say it's 4,000 feet from surface. That's my static fluid level. Actually, I'll take that back. Since the well is only 826 feet deep, let's say my static fluid level from surface is 2,000. My mean ground temperature, let's say it's West Texas at 70 degrees. Stable pumping wellhead temperature, let's say it's 80 degrees. And let's click here on calculate. And the program calculates we need 10,895 pounds to set the tubing anchor correctly, or 10.4 inches of tubing equivalent stretch. So once we set the tubing anchor, we need to move the tubing up by 10.4 inches, and that would set the anchor correctly for this well. So as you can see, the XTOOLS program can be very useful in helping you complete these additional tasks that you need to complete the redesign of a system. There are actually other modules too that might be of interest to you, like the gas anchor designer module, which allows you to calculate an effective gas anchor for this well. If this was a gassy well, you see the SPM is already brought in when I loaded the file. That is my downhole stroke. Let's say my pump efficiency is 85%, and I want to have XTOOLS recommend the design for me for this gas anchor. So it says for a production of 354 barrels a day, the recommended deep tube diameter is 2 3/8. And for 2 3/8 deep tube, the mat anchor recommended is 4 1/4. So I need 16 slots on the mat anchor. I need 4 slots on the deep tube. The deep tube needs to be 12 foot long, and that's my gas anchor design. Another module is the polish rod picker module, which allows you to calculate what polish rod will work in this case. So let's say the length between the carrier bar and the stuffing box is 35 inches. My wellbore conditions are mild corrosive, and the program already brought in the peak and minimum polish rod loads. So if I click recommend here, it's going to tell me that I can use any of these any of these polish rods. I need a 1 1/4 inch Jarrett petroleum alloy steel, or a 1 1/4 Harbison Fisher nickel moly, or a 1 1/4 Norris alloy. Another module that might be of interest to you is the pump slippage calculation, where based on your pump size and your barrel clearance, let's say the barrel clearance is 6/1000 of an inch, and the plunger length, let's say it's 5 feet, we can calculate that normally we would expect to lose 29.23 barrels per day because of that clearance under these conditions. So that's that module, and that completes the process.